Okay, so let's get started. So first of all, um, as we discussed earlier in the semester when we reviewed the syllabus, in week we do have a final project, and then we want to let's discuss the final project before we get started for the regular session. So we have this week is really week 9, and then the idea is you would be forming a team by the end of last week. And also I mentioned that potentially you could have a team of 2, could be have a team of 3, or could be potentially if you want to do that by yourself, you can just do that by yourself as well if the schedule permits. So by now you should have your team formed, and then by the end of this week there's a proposal draft due by end of this week. And then after that, we have final project proposal due actually by the end of next week, which is actually now by the end of in the week of in 2 weeks, which is by the end of the week after. So I actually assume that you don't really have anything that most of the time you don't really need to change anything for your draft proposal. So I'll take a look and make sure that you have the right amount of work, right amount of workload, and right amount of modeling concepts that you would be able to embed into the projects. And then I'll send you an email to say, okay, that's fine, you can just proceed. So potentially you can start working on your project starting next week. Even though we say that we still have multiple homework due, but later semester some of the projects are not as bad as in the middle of the semester. So hopefully you spend more time on the project down the road in the next like 4 weeks, 4 to 5 weeks time frame. So and then let's say in terms of project, you have multiple options. So one of them is you could just take the projects from the textbook. So at the end of each chapter in the textbook, you can find a section titled projects. You can form a team, and then potentially you can select multiple problems. In this case, if you have a team of 2, then you can, let's try to finish, instead of 3 here, let's just finish 2 projects. So in other words, if you have a team of 2, let's try to finish 2 projects for option 1, and then you could select one of them from the first 6 chapters, and then the rest of them, first 5 chapters, and then the second one from chapter 6 to chapter 10. That's one option. And then the second option is select any phenomenon or real world problems. Potentially, if it's it's a problem that's relevant to your business or your current work, that would be even nice. Then you can apply two mathematical modeling techniques to the problem and present your findings clearly in your report and compare the 2 methods. Again, we change that 3 to 2 if you have a team of 2. And then if you are only working by yourself, essentially you don't really need to work on 2 methodology, maybe just one methodology would be sufficient. And then if you're working with a team of 3 and potentially a team of 4, that really happens, then let's target 3 modeling techniques for the same problem. Okay, that's for option 2. And then option 3, you can select one from the project section at the end of each chapter and use the method described in the project, and one additional mathematical modeling methods. Compare the 2 methods is possible. So the difference between option 1 and option 3 is really that option 1, you have 2 different problems to solve and 2 methodologies, because if it comes from different chapters, then it will be different methodologies as well. But option 3 is saying that if you select one problem from one of the chapters, and then you could stick with that data and use the same methodology as required by the chapter, and then you use a different methodology that you learned later in the semester or earlier in the semester, and then apply that methodology into the same problem. And then you can compare those conclusions from both of the methodology and comment on your findings. And then again, you know, each team consists of 2 members. You can also choose to work on a project on your own, or teams 3 or 4. A rule of thumb is if you're working on yourself, you only need 1 methodology instead of 2 here. So let me revise this and give you guys an update as well. If you are a team of 2, let's try to finish 2 methods that we discussed in class. And then again, if you look at the general schedule, this section I forgot to revise. I forgot to revise this part. But the idea, actually in earlier of the syllabus, I do have those timeline laid out. The idea is really that project proposal draft by end of this week, and then final proposal by end of week 10, which is next week. And then I think actually here I just realized maybe something is not quite aligned. Yeah, here should be yeah, let me send an updated version to you guys. The draft is this week, and then proposal is really by the end of next week. So in this case, as I just said right here, you just do the proposal draft by end of this week, and then we discuss and further improve the proposal, and you submit that proposal by end of next week. And potentially those 2 can be identical. I do have a placeholder in the Blackboard system, so you should submit both, even if it's identical. And then for next thing about the project is you need to prepare presentation slides. Again, here somehow really I forgot to update these dates. But it's really the one that it should be Tuesday. Let's be precise there. Yeah, project presentation slides due on December 6th, 7:30 because our class started at 8, so I can put everything together, and then you guys can start do the presentation on the 6th. And then potentially, if we would hopefully we would be able to get it done in the same session. Most of the time we would be able to get it done. It potentially can be a little bit late for that day, so just be prepared. And then by the end of that week, you could just submit your final project report. So potentially, when you started that presentation, you probably haven't finished that report yet. So that should be okay. So again, I'll just update the syllabus so that you realize what's happening. But this table will really give you the exact idea on what the plan is. You would do the presentation on December 6th and write up the final report by December 10th. And then what am I expecting for the final report? Again, let's start with the presentation first. Presentation shall be less than 5 to 10 minutes for each team. It will take place on December 6th, 8 o'clock. create an 8 o'clock through GoToMeeting. And then a project report, feel free to explain the problem you are trying to solve in your report, project final report. It would be great if some of the following questions issues would be addressed. Analysis of the problem, the methodology you use, detail of the methodology, the findings from the project, are the different from your initial expectation? If so, is there a possible explanation? So I'm not looking for a long report. It can be as compact as 3 pages, can be as long as 5 pages. Of course, if you want to submit a longer report, that's totally fine as well. You can attach some of the analysis to the appendix if you want. The idea is really that you get a real problem and try to solve it using the methodology that we studied here. So any questions on project?
Yes, Professor. Can you hear me okay?
Yes, I can. Go ahead.
I'm sorry, I just stepped away for a bit, and I'm not sure if I got everything. I think I was a little confused with the timetable and the schedule. I was not able to find a team member, and I submitted a proposal as for option 1 on Sunday. So that would be fine, me working through option 1 by myself, or I don't know if anyone's here in the class who would want to jump on with me, or I can jump on with them. But it's okay with me working by myself. I mean, I can easily do that as well. It sounded like it may not have been managed before.
Yes.
Is it mandatory?
No, it's not mandatory. So you can work on on your own, and you just need to select one methodology. Yeah, I should update my syllabus, and I think 3 probably is too much for a team of 2. So based on previous experience, would be just 2. So if you are working just by yourself, just pick 1 project instead of 2.
Okay, so I will go ahead and resubmit my proposed, because I outlined the proposed problems I was going to do. Kind of copy and paste them into PDF. So I will, I guess I'll redraft that and send it to, as I said, if anyone's in class here and would want to jump on with me, or I can jump on with them, just please send me a message. Okay.
Sure, you guys can. There's a team formation on the Blackboard. You guys can discuss there as well, or you can respond offline, whichever works. And then you could potentially just work on your own as well, just one methodology. Just realize that this week is really already week 10, so yes, if you already submitted the draft, I would be, should be sending you an email before the Friday, just to give you a heads up on whether I suggest you narrow down the problem or expand a little bit. So that's the real idea there. Okay. Again, I'll update this syllabus, especially this proposal. It should be really due by end of this week, so that you. I think something is in this version is not correct. So proposal is really due here, because you already have a draft, and then once you have that draft, this final versus the draft is like probably 10% more or 0% more. So as long as you submitted last week already, it should be fine. And then I can update this date on the proposal itself, and then I would update that wording of 3 to 2 chapters, and then I'll just send another message to you guys so that everyone's on the same page. Okay, any other questions regarding the syllabus? I mean the project. No? Okay, so if you don't have any questions, then let's just continue and continue with what we planned for the past 2 weeks. Okay, so for last week, it's really, I think by this time you probably already started. So it's chapter 10, game theory. And then game theory itself, at least from this perspective, it is really that when we have 2 or more players, then you have to think about game theory because each individual have different payoff by doing some different strategies, right? Previously, we discussed decision theory, that you have decision node, you have probability node, and then you want to make a decision on what to do, what your final decision would be. But in terms of 2 or more players, it is really the game theory coming into play. And then one of the subcategory of game theory is something called total conflict type of games. And then for total conflict types of games, potentially you could have a pure strategy solution or mixed strategy solution. And then another branch is really partial conflict. So the focus for majority of discussion we have is really on the total conflict. And then here, as there's some discussion, a pure strategy is a course of action available to a player. The strategy is chosen by each player, lead to outcomes with payoff for each player. And then we have definition on what is dominance, and then there's some sort of dominance principle, and the definition of Nash equilibrium. So it's important to understand what is a Nash equilibrium. Nash equilibrium is really an outcome where neither player can benefit by departing unilaterally from its strategy associated with that outcome. That is saying that if user A decided to change his strategy, and then user B would respond with different strategies so that user A utility function would now be maximized. So in that case, we call it if you unilaterally trying to switch to your strategy, to change or switch your strategy, then it's not going to happen that just because B will change his corresponding strategy as well, and then you have to think about new ways to deal with B's strategy, and then at the end, you come back to the equilibrium point, which is really the best strategy that you could take. That would be the Nash equilibrium. And then for total conflict, if for each possible outcome, the payoff to each player sum to the same constant, it's 100 in our example. For example, the payoff of doing A versus B, and at the end of the doing action 1 or action 2 for user A, and then the payoff should be 100%. And then this type of game is classified as total conflict. And then unfortunately, I tried to open my textbook. Somehow I lost the access. I wouldn't be able to show you, but hopefully you already saw that. And then the arrows that goes meaning that if A did this, and then B would do something else, and then at the end, A have to come back to some sort of equilibrium, and B would settle on that equilibrium as well. That type of movement is called movement diagram. And then for any game, we draw a vertical arrow from the smaller to the largest row value in each column. So again, here you try to draw a vertical arrow from the smaller to the largest row value in each column. Look at the column and draw that arrow, and then we draw a horizontal arrow from the smaller to the largest column value in each row in terms of its payoff. And then when all arrows point to a value, we have a pure strategy Nash equilibrium. So that was that solution. Again, unfortunately, I don't have access to a textbook. I tried sometime this week, it just didn't work. I need to talk to the textbook provider and see what's happening there. So that's pure strategy, and then potentially there's some in total conflict games you could have mixed strategies, and then in partial conflict games there could have 3 different ways without communication, with communication, and with arbitration. So that really gives you a high level of understanding of what game theory is. So hopefully by this point in time, I assume you guys already actually have understanding of it already because you already submitted last week homework. So and then in the textbook we try to look at for the baseball example, look at the batter versus pitcher, and then try to understand how can we maximize the objective function of batter's decision. And then in that case, we would be able to translate that game theory to a linear program. That is to say that we're trying to maximize batter's decision, batter's payoff, and then with the corresponding pitcher's strategy, and with the constraint that this utility is less than or equal to pitcher's fast strategy, and also is less than or equal to pitcher's curve strategy. Of course, the X decision has to be between 0 and 1. That's another constraint. So we translate that game theory problem into a linear program problem. So that's why it's connected. That's why, in some sense, game theory also belongs to the optimization families of problems. And then based on that, we would be able to find the optimal solution when x equal to 0.5, and then the utility of the objective function becomes 0.25. And then here is the objective function maximum that we found at this point, and then with the corresponding constraints there. And then in the textbook also discussed a little bit about sensitivity analysis, in the sense that how can we look at this linear program, how can you do some sensitivity analysis, which is idea is essentially identical to a linear program. And then other than that, because in linear programming we said, okay, we could use algebraically to solve linear program. So you try to find some of the extreme points and then try to solve that solution. And then at the end, this one of the ways here you will see that because we have those extreme points, we evaluate the feasibility of those extreme points, and then try to come up with the objective function value, and then pick the highest, in this case maximum problem, so we want to pick the highest payoff of the problem, and then you pick the 0.5 being the solution. And then we further discussed that, okay, what if from the other end, from pitcher's decision, we want to minimize this A that we defined, and then we for batter's different strategy, A has to be larger than or equal to that corresponding payoff. And then Y is between 0 and 1. We try to say, okay, what would be the decision for pitcher? And then similarly, turns out to be that the optimal solution occurs when Y is 0.25 0.25 and the objective function being 0.25 as well. And then correspondingly, we can do sensitivity analysis, and we could solve the problem algebraically and come up with this final conclusion that y value should be 0.25 and the objective function is 0.25. That's really the optimal solution because this one is a minimization problem instead of maximization problem. And then in page 401 of the textbook, it essentially tries to say that, okay, how can we explain this this problem? It says, okay, because correspondingly, if pitcher has the probability of throwing a fast ball versus a curved ball have different probability using an x and y minus x, and then batter could respond with fast or curve with certain payoff 0.4, and because of this probability here, fast being x and fast of batter being y, then the probability for this branch is really just x and y. You can see here. And then for the second branch, the probability is x times 1 minus y, and with payoff of 0.1. And then, so based on this, you kind of get a sense on the connection between game theory, some sort of decision tree, as a linear program as well. And then there's a different example on the textbook talk about Firm's decision as well. And also economy versus nature, I believe. What you need to do in that sense, really not too much to talk about. And here, a very similar thing as a pitcher and batter problem. How can you come up with an optimal Firm strategy? Try to use, you can see the formulation of this problem is really very similar to what we just saw earlier. Of course, there has a typo in the textbook. X should be less than or equal to 1, meaning x between 0 and 1, and correspondingly with different economy strategy, the firm should make a different decision. And then the same thing again in different scenario, what would be the optimal solution? And then for the economy, same thing. To find out minimization of that problem. And then there are some other examples there, like investment strategy, and very similar to the firm and economy game, same as what we have just discussed earlier for the pitcher problem as well. And then, so beyond this, anything beyond anything prior to this point is really give you a high-level overview, and also give you a connection, give you a sense on what is the difference between game theory and how do you be able to, between game theory and decision tree and potential linear program, and how do you be able to translate that game theory problem to a linear program problem. And then starting from 10.4, there's a new discussion on, for pure strategy solutions, how can you use some sort of heuristics that comes up called maximing and min-max methodology to find the optimal solution. So, in this example, let's think about what is the max-min and the min-max. So the max-min, so here is that example in the textbook that says, if Home Depot put a store in Live City and Ace put a store in Live City as well, the payoff for Home Depot is 60. And then if Home Depot put a store in Large City but Ace put a store in Small City, then payoff for Home Depot is 68. So that's the idea of the example. So now you realize that max-min and min-max method is to say that you pick the maximum for each column. So in this example, you can say that maximum for first column is first column for large city is really maximum is 60, and then the maximum for the second column is 68, right? And then after you pick those two, you try to look at minimum of each row. The first row, the minimum is 60, and the second row, the minimum is 52. And then if it happens that maximum, min and max and min happen to be the same value, then we know we found our best strategy. And similarly, you can use same methodology, something called min. Here, actually, max and min and min max together. So if you look at this example, say, okay, when the maximum and max and min max values are the same, the resulting outcome is called saddle point. And if the game has a saddle point 60 in this example, this gives the value of the game. Players can guarantee at least this value by choosing the max and min and min max strategy. So this is a solution that you would be able to come up with use this max min and min max method. And similarly, we have this picture and value example, and then you would use similar methodology to come up with max min and min max. Unfortunately, here you can see that it's not the same, so meaning that you cannot find a saddle point in this example. Again, the row minimum is for the first row is 0.2 and second row is 0.1, and then maximum for the column for the first column is 0.4, but for the second column is 0.3. So that minimum of the max is 0.3, and the maximum of the minimum between those two is 0.2. So we are not able to find a saddle point in this case. So, and then if you look at the movement diagram, essentially here you can see that it point to somewhere which happened to be 16. But in this case, you wouldn't be able to find a saddle point. Okay, we have discussed this already. And then textbook further actually discuss some other methodologies as well, which is really not too much of a focus in our discussion. It's talked about partial games, how do you Prisoners Dilemma is one of the famous examples for game theory, and then talks about without communication, with communication, and all different scenarios. And then that's pretty much the key message that we want to deliver for our game theory section. And then it has very good examples, especially the bad picture, and then how do you be able to translate to linear program. And the next question is, other than the movement diagram methodology, would you be able to find a methodology using minimax and max and min type of methodology to find the saddle point? Saddle point essentially is the same as the Nash equilibrium. Okay, so here is the homework for that section. Any questions, you guys? Okay, so let's continue with this section. So this section talks about modeling with differential equations, and then it talked about some of the examples, use population growth, prescribing drug dosage and braking distance example, and also graphical solutions of autonomous differential equations. And there's some numerical approximation methods and separation of variables and linear equations. So as you probably understand, as you probably learned this in college, during your undergraduate studies, what is a differential equation? You start with difference equations, right? So delta p is a time t plus delta t, the corresponding response p minus the response of p at time t. And then this delta p can be represented as a linear function of delta t, and then delta p equals to k times p times delta t. And then once you do the linear separation, use delta p divided by delta t, meaning that you move delta t to the left-hand side, then what left off on the right-hand side is kp. And then, as we know, if we limit the denominator to approaching 0, then it's a first-order derivative, which is dp over dt equal to kp. And then, so essentially, if you look at the bottom graph, if you look at ds over dt, which is limit delta s over delta t with delta t approaching 0, then it is equivalent to the rate of change, which is the slope of the specific point, right? So if you look at this example, if I pick up a laser pointer, so you can see that at this point, this delta s over delta t is really the slope of the point, which is tangent line at this point, especially when delta t is very small, close to 0. Meaning that if we separate the whole spectrum of t into smaller pieces, each of the piece is close to 0, then we could get this relationship, and then we know the derivative is really the rate of change. Again, we already discussed here. We said, okay, the derivative is really the slope of the tangent line, because if the delta t is really small, then the change of the y-axis divided by the change of x-axis is a tangent line when delta t is very small. But when t is not small, as here this graph indicated, it's no longer a tangent line. It's something called secant line. That is, it's not tangent to the points that we discussed. And then there's this example about population growth that says, okay, at the time t, suppose that the population is really pt, and then there's certain probability, certain rate that the pt would be increasing with certain rate of b. So in time, this time difference of delta t, there is a rate of pt population growth plus this E is the birth rate, and then you would formulate your population for next period being pt plus b times pt times delta t. And meanwhile, you know that there's some deaths in the population, so that minus c times pt delta t, and then you can get your population at t plus delta t. And then once you have this equation, you want to do very similar things that would be try to solve the problem. Then and also it also mentioned that another potential way to look at this problem is the change of population over time is a function of starting point of the population, previous period population, times B minus Cp, the birth rate and the death rate. So that you have this, if you consider that B minus Cp a constant, you can use a K as a constant to represent the equation so that delta P over delta T equals to Kp in this example. And then once you have this, you will be able to know how to solve it. So the way you can solve it is really that you can use the you know that delta P over delta T, if you do the integration, then you get which is log P, meaning that log P derivative would be dP over dt, right? And then you would be able to solve your P, and then log P equal to KT times, okay, sorry. So it should be really this, right? Delta P, you just put delta P over P equal to K times delta T. And then you do the integration. And then once you do integration, the one on the left hand side becomes LP because log P derivative is delta P over P. Well, delta P over P. So and then you use K times T being the right hand side as a constant, because if you take the first order derivative of this function, you should be able to get there. As you notice, integration is a reverse operation of derivative. Okay, so once you have an initial solution with this relationship of LP equal to KT plus C, then you would be able to come up with the solution of that PT is really a function of P0 and exponential growth function of time that elapsed from the beginning of the period until the period in discussion, which is T minus T0 in this example. And then the textbook further discussed how to refine the model to reflect limited growth. Earlier example, we don't have any limited growth, meaning that K can go anywhere, can be as big as it can grow. So we don't really have any can be very big, can be very small, can be even potential, can be negative. But here we say, okay, what if we have a population growth limit, and then we assume that proportionally factor K is not no longer constant, but the rate of population growth K is equal to R times N minus P. N is really the upper bound that you can go up to for the population. And then you do the same thing, same type of manipulation of the relationship. You can solve the problem of PT and solve the problem so that you know at a certain period of time what would be the population, knowing that your initial condition of P0. And the example of the prescribing drug dosage and breathing distance are all identical to what we just discussed. So, and then we're going to go through a little bit about how you can separate a variable, how you can solve the problem, which is more fundamental. Hopefully that helps you. And then in terms of understanding these examples, I think it's essential. Once you look at the example, understand it, you just feel comfortable with this approach. And then also the maximum breaking distance. Yeah, I actually think that we have some example of the separation of variables. Unfortunately, I don't. Oh, it is actually in the next section. Okay, so now before we move on there, just want to give you an example on how potentially you could solve a problem by a methodology called Euler's approximation. So the idea is that you try to update the value tx based on the initial value y0 and plus this g. This g is really the slope of the tangent line at this corresponding x0 and y0, and then times the next value is x, and then x minus x0. Use this slope times the difference of the x-axis from next point to current point, which is x minus x0, and then times this, use that slope times this difference plus the original value of y0, so that you would be able to find what is the corresponding y value for x, for next x. Okay, that's Euler's approximation. You can see that on the bottom chart you can see here, it's really saying that if the true solution is the bottom line, and then using Euler's approximation, using that update function that I just discussed, you would be able to have the approximation corresponding in x1, the value is y1, and in x2, the value is x2. In x2, the value of y is y2, and in x3, the corresponding value is y3, and then the approximation in this example looks is somewhat different, but in reality, if you pick your delta x really small, and then you will find that your Euler approximation is very close to the true solution curve. So this is the example. This happened to be one of the homework problems, and I hope you could actually pick this problem because it's straightforward, but give you an idea on how this can be applied. And then let's look at separation of variables, how we can solve the linear first order equation that we just saw. So in this type of example, so let's look at, okay, how can we solve the first order equation in standard form? What is standard form? Standard form says first order derivative of y plus px times y equal to qx. In this case, what you can do is you start with the separation. So essentially that is you put your x on the one side and then put your y on the other side. If you to solve this, then what you do is, hold on, let me think. I remember that it should be because y is really dy over dx. Now I think I kind of get it. So that is really what the relationship is. This is really in the appendix. So that's why at the beginning of the semester I asked you to go through the example of the appendix. So that is the part that we use in this section. So once you translate that original problem to here, next thing that you need to do is do some sort of manipulation, which is how can we separate this? So the idea is really put x on the one side, y on the other side, I think. But here the thing is, it's similar to what we just discussed here in this example. To put delta p and delta t on different side. But here the problem is it has this term that's much harder to deal with. So let's say I take integration of this. Ux is exponential of that. No, unfortunately, I don't have the textbook, so I wouldn't be able to go through this example at the moment. But hopefully, you will be able to take a look there. But again, if you feel any problem, you meet any problems, send me an email or look at the derivation process of the appendix. The idea is to separate x and y in left-hand side and right-hand side, and take the integration and try to solve the problem to find the solution. Okay, so now this is just an example, and then find multiple linear equation examples in the textbook as well. So here I'm not able to show you exactly what that is from the textbook. Unfortunately, I don't have access this week. And then you can look at the uniqueness of the solutions in the example as well. And the whole idea is how you can solve a differential equation to solve your problem. Okay, that's pretty much what I plan to cover for today. And any questions? Okay, so if you don't have any questions, I just want to reiterate that the importance of the proposal. So your proposal should be submitted today. Submitted by end of this week for the final proposal, and then for the next 4 weeks, homework 14 is really already given, solution is already given, and then you only have 3 more homeworks, and then one of them is rather simple. So hopefully you have more time to work on your project. Okay, so let's stop here today, and then I'll see you in 2 weeks. Have a good night.